In week 7, okay. So as I said, today we're gonna finish by Stokes theorem and the divergence theorem. Okay. So we talked about oriented surfaces, that a surface that is closed has, right? So we said that if a surface is closed, then the positive orientation is always the one that goes outward, right? But only if it's closed. So if each, each time you have a closed surface, the orientation for n, these are the vectors n, that are normal, right, to the tangent plane. You always take the vector that points outward. So what is Stokes theorem? Well, Stokes theorem, there's nothing new in terms of the concepts. You already know everything you need to know. You already know what is a surface integral. You already know what is a line integral. You already know what is double integral over a surface. All of those things, you know that we're gonna just gather them together, and it gives a theorem. So let F be let F be a vector field on R3, okay, and S an oriented surface with boundary C. Okay. So the orientation on S induces the positive orientation on the boundary curve C. So remember, a positive orientation on a curve is counterclockwise, right? When you see it on a plane. Then we have the following theorem. So concretely speaking, what does it mean here? It means that if I have a surface, right? If I have a surface here with this orientation here, okay? What Okay. You choose an orientation for n. Then you can use an orientation on the curve here. In this way. So this is the boundary curve. And this is the boundary curve. Okay. And this is a surface. Okay. So this is a surface and this is a curve. And this orientation induces an orientation on C. Okay. And now we can speak about and I have a vector field everywhere. This is R3. Okay, and I have a vector field that is defined everywhere. Like, right? Specifically, it's defined also on the surface. Okay? And also on the curve. Okay? So we have the following theorem. It says that let S, so this is S, be, well, here are some technical parts. Let S be an oriented surface, piecewise, smooth surface that is bounded by a simple, remember what is a simple curve, meaning that it doesn't cross itself twice. Closed, meaning that the first and then the first, the point, the starting point and the terminal point are the same. And piecewise smooth, meaning that the first derivative does never vanish except maybe at some finite number of points, right? This is a smooth, this is piecewise smooth curve. Smooth curve boundary, piecewise smooth boundary curve C with positive orientation. Okay. Let F be a vector field F the vector field whose component have continuous partial derivatives from an region in R3 that contains S. So for this kind of assumptions, you don't have to worry that much about them. They are just really there because the proof works when you have these assumptions, right? But in all practical cases, as I was saying from the beginning of the class, these assumptions, they'll be automatically verified. So what we have is that the integral over the curve f dr is equal to the integral over s, the curl of f ds. Again, in other words, it is also equal to the boundary, the integral right? Because these are the same. So this is the boundary of the curve, the notation. It's a notation thing. So it means that if you want to do the line integral of f along the curve C, you can, instead of that, you can do the surface integral of the curl of f on the surface S, right? So this means that if you have another surface and it has the same boundary, then computing the surface integral over this new surface is going to be the same because they have the same boundary. If they have the same boundary, then the surface integral of the curl is the same. Well, that's a pretty much good theorem, and you'll see some applications of it. So we can prove this theorem in a very specific case, but let us just first see how we can use it. So first of all, let us see that Green's theorem, the one we saw previously, is actually hidden inside this Stokes theorem. Okay. So now, what is Stokes theorem? So Stokes theorem deals with, remember, with 2D surfaces. Oops, with planar regions, right? So we have C, positive orientation. We have a surface S, right? When we are in X. Now the thing is, this the Z-axis here, right? There's the Z-axis. that points towards you right now. So, but the surface lies on the xy plane, and we have a vector field F that is pi plus qj, right? Now, be aware that when we introduced Green's theorem, we were only aware of 2D vector fields. Now this is a 3D vector field. It has no z component, right? So we are in 3D here. We're not in 2D, we are in 3D, okay? So we can apply Stokes' theorem. Then by Stokes' theorem, we have that the line integral of f dr over c. Now this is the surface, right? This is the surface. Okay? This is our surface now. Now what is the boundary of this surface? The boundary is the curve itself, right? It is a simple region and everything is okay. So the boundary is the curve itself. So this is equal to the integral over s of the curl of f ds, okay? Now, what is ds? Remember what is ds? ds is always the normal vectors times ds, the scalar element of surface that you're going to compute. Either it's a parametric surface, in which case you'll have to compute the norm of the the cross product, right? Or if it's a graph of a function, then you just take the square root of 1 plus derivative with respect to x plus derivative with respect to y. So this is just a computation that you're going to get, but it's always the normal vector times the element ds. But in this case, the normal vector is k, right? It's a vector field because it's a surface that lies on the xy plane. So what is the normal vector? You don't need to compute it. You know, normally what you would do is you would take the parametric surface, compute RU, compute RV, take the cross product, divide by the norm, and that's gonna give you n. You plug in here, and that you do the calculation. But here you don't have to. You don't have to because what's the mean of n? It's the vector that is normal to the surface. But here the surface is a flat region. It's a flat surface that is on the xy plane. So we automatically can say that the normal vector is the one that it's k. It's the one that points towards you right now, like here, right? This is a notation from physics. No, I don't think mathematicians they use it, but when you have a circle and you make a point instead of, because when you do this, meaning that it points inward, right? And when you do this, it means that it points towards you from the page. But this is not used anywhere. I use it. I mean, I didn't use it. I mean, use it from physics, but this is just. So the normal surface points towards the z-axis, the positive z-axis. So it's k times ds. Okay? Now what is the curl? Now the curl, you just compute it. It's I, j, k, del x, del y, del z, p, q, 0, right? You do the calculation and it'll give you what it'll give you, right? I'll give you, here it's gonna give you okay, these are functions of x, y. Yes, I remember. Yeah, because we are in the case of Green's theorem. So these are functions of x, y. It doesn't depend on the z. It doesn't depend on where you are, right? It's a vector field that is on the xy plane, and it looks the same everywhere. So we're just in the setting of Green's theorem. So this one gives 0, and this one gives 0. This one gives 0, and this one gives 0. So the only one that is left is dx q minus dy p k, right? So the integral dr is the integral over the surface S of dx q minus dy p k scalar with k dx. Well, these two are one. Okay, so this is ds. Okay, and in this case, ds is dA, right? Because again, don't be confused. I know it's a bit confusing, but in the beginning we were using dA, right? But it's only for the 2D case. Remember, dA was used when you have a flat region, when you have a projection or whatever. We use dA. But when we were in the in the in the in the 3D case, now the surface is in 3D. So we used, instead of dA, we used ds, right, to make the difference. So here it's really dA, right? It's really dA. Right? Because you always have to remember the meaning of what you're doing. ds is just, if you just compute what is ds, it'll give you dA, right? Because again, I mean, you can do it really rigorously if you want, because now uh, the you can really do it like rigorously if you really want. Like if you want to prove that ds is dx dy, you can do it just by what is the surface? Surface is just some, right? You can do it, but I'm not gonna do it here. But uh, you you can you can just, this is the, because you have to think about the meaning. It's an element of the surface. So in 3 cases ds, but in 2D cases dA. Now what is FDR? Which is just E I Q J times dx dy, right? So we recover Green's theorem. Right? So this is Green's theorem. So this means that Green's theorem has also this form. Okay. So this is kind of another version of Green's theorem. Now let us do something else. Let us do so you remember one of the questions of the quiz was to compute a surface integral, the vectorial one. It was a long one, I guess. I hope so, because we didn't know about Stokes theorem by that time. Like last week, we didn't know what is Stokes theorem. So last question, maybe not the last one, but one of the questions in the quiz was compute a surface integral over a cylinder, and you had a surface. The example is exactly the one I'm going to give you here, but the point is that question was long. Okay, you have to do it on one side, and then you have to do it on the cylinder, and then you have to do it on the bottom side. Okay, and you need to make sure that nothing is wrong and all the calculations are okay. Now, the good news is Stokes theorem is going to allow us to do this in a fraction of a second. I think so. Not a fraction of a second, but much more easier than doing it on each side. Okay. So another example is, okay, let us use Stokes theorem to evaluate oh wait, is this an example of oh maybe that's not the direct, but no, this one is okay, but anyway, it's also a good example for that one too. So to evaluate this one, oh but maybe that one is a okay, I guess so this is not here, it's in the divergence there. Okay. Let us use Stokes theorem to evaluate this integral where f is the vector field x squared z plus xy squared j plus z squared k. Okay, and c is the intersection of the plane and the cylinder So this is the positive orientation, counterclockwise. as viewed from above. Okay. Okay. So this is the circle. And this is the plane. Give me one sec. So we have the plane x plus y plus z is equal to 1. And we have this cylinder. And we would like to compute this line integral. So let's first see if you want to do it directly. If you want to do it directly, it's going to be a bit more work in the sense you have to parameterize the intersection, and you need to find a parametric equation of the curve, right? Which might not be that hard, but still, you need to do it to find the parametric representation of this curve, and then you have to compute the line integral, and there's no reason it's going to be an easy integral, but here we're not going to do it directly. We're going to use Stokes' theorem. So instead of doing the integral, we're going to consider the surface here, right? Right, this is a surface, and it has a boundary. The boundary of this surface is the curve we would like to compute the line integral on. So, right? So first we have the curl of f is I, j, k, del x, del y, del z, okay? Okay, if you do the calculation, it'll give you x squared j plus y squared k, okay? Now, what is the other ingredient you need to know if you want to compute the right? Now, this is the intersection of the plane with the cylinder. So actually this surface is just a part of the plane, right? Now the equation of the plane is x plus y plus z is equal to 1, right? So the normal, but here just be careful because you need to choose the right one, right? So if you were looking carefully, the orientation needs to be outward here so that when you see it from above, it's going to give you the positive orientation, right? Right? When you see it from above, it's going to give you when you see it from above, it's going to give you the counterclockwise orientation, right? Right. So a good rule to keep in mind, and it works to verify your intuition is mm, everywhere. Looking for the positive one. I don't know. Mm, let me check this. But the normal here needs to point outward so that when you see it from above, it's going to give you the counterclockwise orientation. And it's given by 1, 1, 1, right? You read them, right? You just check the coefficients of x, y, and z, and then it's 1, 1, 1. Sometimes it's not 1, 1, 1. It's sometimes it's going to give you what it gives you, but just check from the diagram that it points towards the right direction. But if it was minus 1, minus 1, minus 1, then that's not the right orientation, right? Okay. No, sorry. Then a normal vector is given, right? So a unit okay? Because when you have a plane, what we got was just a normal vector. Now you have to rescale it so it's going to give you a normal vector. And the good news is it's the same one everywhere because it's a plane, right? It's not a curved surface. So ds is equal to n ds, which is 1 over square root of 3, 1, 1, 1 ds. Okay? Meaning that f ds is if you take this and you take the scalar product with this, it will give you 1 over square root of 3 x squared plus y squared ds. Okay, because there is the z component. Oh, yeah, the y component. The y component is the x component is absent. Okay, hence by the Stokes theorem, we have, so if you want to integrate f along the boundary C, you don't need to do that. You just have to compute the curl of f scalar with ds. Oh, here is the curl. Curl of f scalar with ds over ds. And this is equal to the integral over s of 1 over square root of 3 x squared plus y squared ds. Okay? Now, you need to think about the meaning of this. So what is it? We got a surface integral that has to be integrated over the surface S, right? This is a function. This is just a normal function. And this is an element of a surface here. And we need to integrate over all the surface. Okay? So again, there are two cases here. Either the surface is a parametric surface, in which case you have to write everything in terms of the parameters u and v, compute the ru, rv, take the cross product, take the norm, and then integrate over the domain d in the uv plane. Now in this case, it's a graph of a function. Here, what is z? Here, what is s? It's a part of the plane z equal to 1 minus x minus y. For x and y, okay, and x and y are in the projection of f onto the x, y plane, right? Because now, if you wanted, I mean, you can do it really with RU and RV, but we did that last time. So S is a graph of a function. This is z 1 minus x minus y. And x and y, they're allowed to vary from inside this disk here, right? Right? So this is the disk that is gonna give you exactly the surface, right? When you project, that is always the case when I have a graph of a function. If you have a graph of a function, the domain D is always when you project. right? So when you project, we are inside a cylinder, so it's the disk, right? What is the disk? It's the disk x squared plus y squared less than 9. So this is equal to the integral. Now, this is just a function. Now, what is ds? ds is this square root of 1 dz dx squared plus dz dy squared dA, and now we integrate over dA over a over d. Right? So here again comes the notations. dA is when we are on a flat region. Here, this is d, and ds is when we are on 3D. And this is just a factor that lifts, when you lift an element of, we did that in the proof. When we lift an element dA on the surface, when we lift it up, it'll give you a factor and then rescale that element. So now, what is this? This is the integral over d of square root of 3 x squared plus y squared square root of 1 plus 1, I think, plus 1 dx dy, right? Now, this one cancel out by this one. Now we are integrating over d x squared plus y squared dx dy. Now, whenever you see this kind of x squared plus y squared, might be, and we are in a circle, so it's obvious that you need to go to polar coordinates. So this is r squared r d theta from 0 to 1, 0 to 2 pi, which is equal to 0 to 3. Right. This is a radius of a circle. The radius is 3. Okay. So this is 2 pi r4 over 4 between 3 and 0, which is 81 over 4 times 2 pi, which is 81 over 2 pi. Okay. So there is nothing really, maybe the hardest part is just to keep track on the orientation. But a good rule of thumb is when you see the surface, you always make sure that you see the surface so that the normal vector, this always works. You see the surface when n points upward, and then you go counterclockwise. That's always going to work. You see the surface, you reorient it, so you reorient the surface so that n is going to point upward, and then you go counterclockwise with the curve, with the boundary. That is going to give you always the right directions, the right normals, the right signs. The only thing that can go wrong, as I said the last time, is really a -1. If you, for example, if I really wanted to test your understanding, I would give you for example, the equation of the plane as -x minus y minus z plus 1 is equal to 0. Then maybe you can be confused about what is n, right? And so the only thing is going to go wrong is -1 instead of plus 81. over 2 pi is going to be minus 81 over 2 pi. But make sure that always the end is always, whenever you have an orientation, doesn't matter which one you choose, just when it points upward, when you view it so that it points upward, go counterclockwise for the curve, go counterclockwise, and that's the right setting. And this question of this story of science, it's never easy because it depends on the conventions, it depends on what, it's never easy to just, it takes a little bit of time. So we're gonna make sure that you understand everything when you ask a question, we're gonna make sure that everything is clear and you know what is your orientations. Yeah, so maybe when you're gonna prove this theorem, you will see. So the proof is not that hard. So let me take a break. We're gonna do the proof, which is gonna take us very few minutes, and then we'll do divergence theorem. Okay, then be back at 11:23. And I can see here that there is a coffee symbol here, meaning that takes a break, need a break. Oh, this is for the students. No, you always had this. You can click on the coffee emoji, I think. If someone needs a break, I can see it. Okay, back to the proof of Stokes theorem. And we're not gonna prove it in full generality, in the sense that we're gonna assume that C is a graph, prove the Stokes theorem when S is the graph, right? And that this proof also might help you with like going through these concepts again and again so that you can much more implement them into your mind, right? The graph of a function is the graph of a function g x y is equal to z. Oh, did I stop? Is it recording? Okay, and x, y are in some d, which is the projection, and g, x, y has continuous. You will see why this is important. Second order partial derivatives. Okay. Take f as pi uj plus rk as in the theorem. Okay, so the integral over s of the curve of f ds. So here Uh, I'm gonna do it a bit quickly, but what you do is compute the curl of f, okay? And then the parameterization of f will be given by x, okay? Will be given by x, y, and g, y, right? So you can compute the curl, just apply the formula of this. When you have a vector field and you have a parametric surface, apply the formula, like with RU and RV, right? This is Rx instead of RU and RV. Just apply the formula and it'll give you this, right? And here the domain of the parameter domain is gonna be the projection, so it's gonna be D. But the only thing is you have to apply it for the vector field curl of F. Again, the whole thing, dA, okay? So I'm gonna stop here, and I would like it to, if you really don't understand where it comes from, it's very important that you tell me, okay? If you have no idea where this comes from, what did you get, where did I get this formula? You can also use, if you don't want to talk, you can also use these emojis here, like thumbs up, thumbs down, right? I cannot, it's anonymous, so but if you understand, that's okay. Because I already explained it, but I have no idea if you get it or not. So, I mean, it's really the curl of f. You compute the curl of f, which is these three vectors here, right? The curl of f will be essentially these three vectors here. And then the s will be the curl of, right? Remember the formula. You have r, x, and y, right? And you will have to compute rx times rv, right? And then you have to take the scalar product of curl of f with rx, rv. Sorry, in this case, it's going to be ry. And then the whole thing ds. The whole thing dA. Where, and then you integrate over the region D, where D will be the domain of the parameter space. And again, I'm going to repeat it. The parameter space here will be the projection because it's a graph of a function. Right? If it's not a graph of a function, it's not a projection. If it's not the graph of a function, it's just the domain D. UV plane, you have, for example, in a circle, it's 0, 1, 0, 2 p, 0, 2 pi. Nothing to do with any projection. Just so please make sure that you ask questions if you don't understand. Because there is no way for me, and I can guess if it's too trivial for you, it's too easy. Okay, and here we are on the surface, right? Because when you integrate this, remember when you integrate a surface integral, the integrand which is the function that you are integrating, has to be evaluated on the surface, right? Where the functions are evaluated at xy, gxy, okay? So this is a point on the surface. Okay, so this is from, okay, this is, keep this one here, keep in mind. Now, suppose that RT is xt, yt, zt, and t is between A and B, is a parametric representation of C. So what is C? Oh, so I forgot to give you a graph here. So we are in the setting where I have three functions. I have function z equal to gxy, and I have this curve, and I have the normal. And then when you project, it give you okay. Okay, and this is S. And we suppose that our t is some function xt, yt, g, right? And this is C1. Okay. So suppose that is a problem, then C is given by xt, yt, g, xt, yt. Oh, I think there's a typo here. So we're talking about this two-dimensional curve. When you project this surface on the XY plane, it's gonna give you a two-dimensional surface curve. And if this curve is given by xt, yt, then what is c? What is c? Just you go, this is the point xt, yt, then you go the image on the surface, which will be the g of x of y, right? So if you want to go along all this curve, then this is going to be a parameterization of the curve c, and t is between a, b. So I hope this clears, right? So what is this? The FDR. It will be the integral from a to b of p x prime t plus q y prime t plus r. And here, make sure that you understand the steps here. It's g xt yt prime dt. Okay, so here we're gonna use what you've been learning in the first half of the class. It's p x prime t plus q y prime t plus r. Now, this is a function of two variables. And each variable now is a function of one variable. So if you apply the chain rule, this is going to give you the d del partial derivative with respect to x of g dx dt plus partial derivative with respect to y dy dt. Okay. Now, if you reorder this last equation, it will give you p plus r del x g dx dt, right? Because this is also equal to dx dt, right? Plus q plus r del y del g del y del y del t dt. And this is gonna give you the integral from a to b the function p plus r del x del g dx plus q plus r del y. And here we are on the curve C1, right? So if you look carefully, you remember what he did for the line integrals and what is the meaning of this on C1. This is just exactly this one. Okay, so if you just remember the meaning of this, this is exactly the meaning of this. Now Green's theorem. Now we can apply Green's theorem. So by Green's theorem, I mean, there is a kind of catch-22 here in the sense that I gave you an example where we deduced Green's theorem from Stokes' theorem, but we actually used Green's theorem to prove the Stokes' theorem. So I don't know if you got this, but it's really a tricky thing. It's not really, I mean, Green's theorem is still the original thing. right? But we use Green's theorem to kind of inflate, like we inflated Green's theorem into kind of more general theorem, but we just made, what we did is we didn't deduce Green's theorem from Stokes' theorem. We just made sure that Green's theorem is still inside our new theorem, which is Stokes' theorem. So we really, right? It's a really tricky thing, because here we're really using the Green's theorem. But so by Green's theorem, this is equal to, we have, this is the integral over the domain D, right? Because we are now, this is our domain D. And now remember, what is the Green's theorem? You take the partial derivative of the second component of the vector field, and then you subtract the partial derivative with respect to y of the first component of the vector field, which is in this case p plus r dx. But here, it's a bit tricky here, you know. Now, remember, it's a really tricky thing here. Recall that Q, P, and R are functions. This is a vector field in 3D, are functions of x, y, and z. And z is a function of x and y, right? So when you take the partial derivative of, so when you take the partial derivative with respect to x of the function q, x, y, z, it's not the partial derivative of it, no, I mean, the partial derivative with respect to x is not this quantity here. This is confusing, because this one is also a function of x and y. So you need to make sure, I need to take it into account. So this is equal okay. So it's the partial derivative with respect to x of q plus the partial derivative of q with respect to z times derivative with respect to x. Remember the chain rule, right? You have x, you have y, and you have z. And then from z, you have z is a function of x and y, right? Okay, remember the chain rule. You have the function, you have x, y, and z is also a function of x and y. So if you really want to go with the partial derivative with respect to x, right, with respect to x, you have to take this into account. You have to go. So this is the function g, right, of x, y, and z. So you have to go partial derivative with respect to x, and then you have to go just with the partial derivative. This is q, by the way. Sorry. Partial derivative with respect to z, and then partial derivative with respect to x. And this is going to be a function g. Okay, z is equal to x and y, right? You have to go through all the paths to get the partial derivative with respect to x, right? And of course, when z is a free variable, you don't have this part, so you only go once. So that's a trick you do, right? Remember, that was a chain rule. So this is equal to, it's a long calculation here, plus, so you do it for every single function here, because all of them, they are functions of x, y, and except for g, of course, but all of q, r, and p, they are functions of 3 variables, but the last one is a variable that is a function of the other 2. So you do this calculation, it will give you partial derivative of r with respect to x, dg, dy, plus, now I'm applying the same thing for r, dz, dz(x) plus r. Now I'm going to the other one. So this is the product rule. This is just dx. Now it's a function of just 2 variables, so there's no chain rule, right? And now I'm done with the first. Like I'm done with this first half. And I do the exact same thing for the second half, which is del y, del p plus del z p del y z plus del r del y del g del x plus del r del z del z del y del g del x plus r second derivative with respect to del y del x g. Now you have this huge equality here. Now if you compare this one with this one, right? Plus, right? Okay, so here we can use Clairaut theorem plus assumptions. Remember that the second partial derivatives were continuous. So now we can use, so they are equal, like no matter the order. And right? You can also cancel out these two. So what is gonna be left is, so what is left is in 4 terms that's gonna be left. And they will be, if you go back to this, if you compare how many we have here, 1, 2, 3, 4, 5, 6, right? And here you will get 1, 2, 3, 4, 5, 6. Okay, so if you compare these two with the signs and all of that, it's exactly the same, which is equal to when reorder, right? You can go through it, but you'll have just to reorder this one with this one, right? With the sign, and then isolate dz, dx, dz, this, because this is also dz dx, right? And also remember that z is equal to g. And you just have to isolate, rearrange, do some algebra, and it'll give you exactly the same. So this is the proof of Stokes theorem. It's a bit long, it's a bit complicated, but this is the proof. Now, the divergence theorem is going to be much more easier. Okay, so now let us start divergence theorem. The divergence theorem is, so Stokes theorem gives a relationship between the line integral over the boundary of a surface, okay? And the surface need not to be closed, right? And it needs to have a boundary, okay? Yeah. There's also one last example, but I'm gonna see if I can include it, but it's in my notes. But one last example of Stokes theorem, which is, remember when I gave you the rule that says if a vector field is defined everywhere and the curl is 0, then f is conservative. Remember, I gave you this and I told you, look, use it, but then we're going to use Stokes theorem to prove it. Now here's an example. There is an example in my notes that proves this. It's not that hard, right? You just have to prove that the only trick is you need to accept the fact that if I give you a curve, then there is a surface such that this curve is a boundary. Like if I give you a curve, then you can find a surface such that the boundary of this curve, of the surface, is the curve itself. So once you accept that, you can prove that if the curl is f and f is defined everywhere, then it is conservative. And you need to use the fact that, another fact that if it's conservative, then it's the same thing as the line integral over every closed surface is 0, which means that it's path independent, and when it's defined everywhere, path independent means it's conservative. But read this in the notes. Now I want to spend the last hour talking about the divergence theorem. So the divergence theorem is gonna be kind of similar to Stokes theorem, but it gives the relationship between two other species of of integrals. So let E be a simple, and here simple means that it is simultaneously a region of type 1, 2, and 3. Remember, what is a type 1, 2, 3? It means that if it's between, when you see it as a between some z, between some function of two variable and another one, go back and see what is a type 1, 2, 3, right? And anyway, I'm gonna recall what it means when I'm gonna give you the proof of it. Let E be a simple, but keep in mind that a simple means it is simultaneously type 1, 2, 3. Let E be a simple, solid region, right? It is a 3D region and let S be the boundary surface of E given, and here it's going to be a closed surface. So the positive, whenever you have a closed surface, the positive orientation means it's outward normals given with positive outward, mean outward orientation. Okay? Let F be a vector field whose component functions have continuous partial derivatives. Okay? On an open region that contains E. And then we have the following. So if you want to integrate the vector field F ds over the surface, then this is the same thing as you integrate over the solid E of the divergence of E of F dV. Right? So, meaning that if you have a surface, okay, and you have a vector field, and then you have the normal, okay, all along the boundary, then this is E. So this is a function of 3 variables, right? And so if you want to integrate this vector field over the surface, then you don't need to do that. If you can only also do sorry. This is a triple integral. The triple integral over the solid E. Okay? Because these are the function of 3 variables and you are integrating. So let us do an example before. We're going to do 2 examples, and one of them is one I was talking about, the quiz one. And that's going to end our discussion. Okay? Let me do a first example, and then we take a break. Evaluate square okay? So concretely speaking, this means that I'm in the 3D case. And I have this paraboloid here. Okay, and this is a kind of surface, right? Kind of projection. Okay. Okay, this is the parabola we were speaking about. And this is, so when you project, it'll give you the region D, which is x squared plus y squared less than 1, right? So these are the region D, right? And then we have the surface S, given by the paraboloid. And then we have the region E that is inside, okay? So you can compute this one using DS and the parameterization, and it's gonna be another type of computation, but we'll do it using the divergence term. So what is the divergence of F? This is gonna be del X 2x squared plus Y cubed plus del Y U cubed Y cubed Z cubed plus del Z 3y squared Z, which will be equal to, if you do the combination, it'll give you 6x squared plus 6y squared, which is 6x squared plus y squared, right? So by the divergence theorem, if you want to compute this line, surface integral over the surface S, it is equal to the divergence of F and the region E, and this is a triple integral, okay? This is the integral over E of the function 6x squared plus y squared. This sometimes is gonna be a function of 3 variables inside, but in this case, it's only 2 variables, dv, right? So now you just go back to what you know about triple integrals. How can I describe the solid E? All right, so this will be equal to the integral from z equal to 0 to, because what is the surface here? It's z equal to 1 minus x squared minus y squared. right? The function x squared plus y squared dz, and then you'll have to describe the projection dd on the 2D plane, onto the 2D plane. But here it's easier done with polar coordinates, so it's 6. First of all, we're gonna compute this one, which is x squared plus y squared 1 minus x squared minus y squared dA. This is equal to 6 r cube r squared 1 minus r squared r dr d theta from 0 to 1, 0 to 2 pi. Right? This is the circle. This is the disk, right? It will be equal to 6, right? Integral 2 pi, integral from 0 to 1, r cubed 1 minus r squared, right? Which is equal to r cubed minus 4r5 dr, right? And 2 pi r4 over 2, right? Between 1 and 0 minus r6 between 1 and 0, which is 2 pi 3 over 2 minus 1, which is pi. Right? Make sure that it's supposed to give something positive because you integrate over a volume of something positive. So it's supposed to give something positive, which is okay. Right? So that's one type of computation. Let me do that. So the last example will be uh, another example that illustrates how this divergence theorem can be used to avoid a long calculation as the one in the quiz, where you have to do the surface integral over 3 regions. And in this case, it's going to be 4 regions. But I'll do this after the break. Be back at 12:20, and maybe this one is going to take us 10 minutes or 15 minutes. And then the proof isn't that much. Yeah. And then there is only one last thing, but I don't think I have time to speak about, but it's a kind of application of divergence theorem that tells you that the meaning of the divergence theorem, what it means in physical applications, which is in fluid dynamics, like when you have a sink or you have a source and you have fluid that goes around a tube, for example. So it gives you kind of divergence, a kind of measure of, is this point the source of the fluid or it's kind of attract the fluid? So it's kind of, is it the sink or the source of the fluid? So this is another type of application of this theorem. But you can read that in the notes. But my hope is I'm gonna finish the example and the proof, and that's it. So we'll be back at 12:20. Okay, so let me back. So only 5 people, I guess. 4 people are left. So hold on. Still maybe only 60 minutes, only 40 minutes left. So you're gonna be a really, really awesome warrior after these 40 minutes. So I know it's not easy to attend class from home. Sometimes it's very boring and not very stimulating. I know that. And there is no that kind of personal interaction. So okay, so let me do the last example. Evaluate the integral over s of f ds, where the vector field is x, y, I plus y squared plus e to the power xz squared j plus sine of xy k, okay? And S is the surface of the region E bounded by the paraboloid cylinder z is equal to 1 minus x squared, and the planes z equal to 0, y equal to 0, and y plus z is equal to 2. Okay, so here we have a paraboloid cylinder. Okay, okay, so it goes parallel to the y plane, to the y axis, right? We have z equal to 0 in the bottom. We have y equal to 0, okay? Which is this one. And we have the surface of the cylinder, and we have the last plane that is gonna go like this, right? Because it's a it's a plane that is in the y. Let me see. It's a plane that it's a plane that has. If you see this one in the YZ plane, it's a line. So when you go parallel to the X, it's gonna be some kind of plane that goes like this, right? So it's gonna cut off the the, the, the surface of this paraboloid in a certain sense, in this way. Okay. Oops, sorry. Oh no. Oh no. Oh no. Oh no. What just happened right now? Okay. Ah, okay. So this will be the, so our surface will be this surface here, S. So this will be E, this will be the surface S. And then we would like to compute this one here. So remember the quiz, you have to do it on each top, right? You have to do it on the lid, you have to do it on the bottom side, you have to do it on the cylinder. This is a different kind of cylinder, but it's the same concept. And then you have to do it on each side. So it's gonna take you a really long time to do it. But if you do the divergence theorem, what is the divergence of this field? You just apply dx to this one, dy to this one, dz to this one. And it's really easy. It's just, if you apply, this is x plus 2y, and this one is independent of z, so it's 0. So it's 3y actually. If you did partial derivative with respect to x is y. So this is 3y. So already the divergence is very easy. So the integral of f ds of the region S here is the triple integral over E of the divergence of f dv. Okay? And now we're gonna see this. What's the easiest way to see this? You have to see it as a type 2 region, right? Because if you try to do it, you can also do it as a type 1, but it'd be easier to projection, but you will have, you can also do it as a type 1 region, possible. But the only problem is you will have to split it into two. It's going to be very complicated if you do it in a type 1 region, because here it's the surface of the plane, and here it's the surface of the cylinder. But if you do it as a type 2 region, meaning that you go like this, you see it like this, like, and then the z will be the y. So now for each point, you go from 0 to the top, right? So it's, what is the divergence? It's 3y. Now you integrate with respect to dy. From 0, this is the plane, z equal, this is the plane, y equal to 2 minus z. So 2 minus z. And then you describe the projection, right? So what is the projection now? This is the integral from 0 to 2 minus z dy dy. Now you have the choice. It's the projection is this one, is this region here, right? Now you have the choice. You can either use type 1 or type 2, right? It's not a problem. So, but the easiest one is to just go with type 1, meaning that z is between, this is 0 and this is 1 minus x squared. So dz is between 0 and 1 minus x squared. Now dx is between minus 1 and 1, because you have to look at these intersections here. Right. So that's it. I mean, once you do this, it's all the computations. And this is very routine. This is 3, right? Integral from minus 1 to 1, 0, 1 minus x squared, right? 1 over 2, 2 minus z squared dz dx, which is equal to 3 integral from minus 1 to 1 of minus 2 z over 6 cubed dx. Like if you do it carefully, it'll give you 1 over 2 integral minus 1 to 1, 8 minus cube. Okay, yes. Okay, this is minus. So give me 1 second. I'm just gonna check that. Save. I just forgot to compute it, so I just want to make sure that I have the right answer. 8 minus 1 plus x squared to the power 3. Eight minus okay. Okay, so just do it. Nothing hard, you just compute it. In 184 over 35. Okay, so that's the answer. Okay. Okay, so that's it. That's the kind of calculations you'll be doing. Nothing really new. You just have to know when to apply it. I mean, if you know how to do triple integrals, how to do surface integrals, it's just, theorem is just a way to go from one side to another side. Now, of course, there are some good applications of this, and I tried to include one in the assignment. And in the assignment, by the way, if you look, there is one question that says that one question has to satisfy if L squared is equal to -1. Don't be scared or intimidated or being kind of suspicious about the credibility of this course. Well, this is real actually. That in mathematics, it's possible to have a number such that the square root of it is equal to -1, but it's not something that we cover in this class. But this number here, you're gonna have it in an expression like this, right? So when you take the derivative of this one with respect to x, even though this number has to satisfy this kind of strange equation, you just take the normal derivative, just lk x, right? Normal way. And then you see this L as just a constant number, right? In the mathematics, we call it I. It's an imaginary number, but it's a constant. So now let me finish by proof of divergence theorem when E is a simple region, meaning that it's simultaneously a type 1, 2, and 3 region. Right? And this theorem is going to be a little bit more easier. Let F equal to Pi plus Qj plus Rk. Okay? Be a vector field. As in the term. As in the theorem. Okay? Then the integral over E of the divergence of F dV will be equal to the triple integral over E del X P dV plus I don't know what's happening today. I really don't know. Okay, dz r dv. Okay, if, oh my God. Okay, if n is the unit outward, remember we always take the outward one, outward normal of S, then we have right, what is the integral of F ds right? So now go back to, okay, no, it's okay. Pi plus Qj plus R. Okay, you see that this proof is a kind of reminder if you're still struggling with the concepts of what is to be done in case of a normal. So here is the normal times ds. So this is the integral over S of P I scalar with N plus Q J scalar with N R K scalar with N, and whatever this gives you, you just integrate over S. Now you can use the fact that these integrals, they can be split off into 3 parts. Okay, so we will prove that the integral over S R K N ds is equal to the integral over E of dr dz dv. Okay. Okay. The other equalities are proved in a similar way. Okay, in the sense that if you prove that this one is equal to this and this one is equal to dr, right? Go back here, and this one is equal to dq dy, and the last one, the first one is equal to dp dx, then you prove divergence there. So we're gonna prove one of them. So for this one, that's why we are supposing that the solid is simple, because for each one you're gonna use the fact that it's a type 2, 3, or 1. So for this equalities, you're gonna rewrite, you're gonna write E as a type 1. For the others, you're gonna need type 2, and the last one, the first one, you're gonna need type 1, type 3. For this one, you're gonna use the type 1. So we use the assumption that it's a simple solid, so x and y are belong to the projection onto the xy plane, and then z is between some two functions u1 xy and u2 xy. Okay, where v is the projection of E onto the xy plane. Hence, the integral. So what is the integral over E of VR dzr dv? This is the integral over the domain D, integral between u1 xy, u2 xy, r xy z, right, dz, and the whole thing dx dy. Now, by the first fundamental theorem of calculus, this is r x y evaluated at the point u2 xy minus r xy u1 xy, and the whole thing, this is r, is dx dy. Okay. Now let me do some kind of graph here. So what is our assumptions here? Assumptions are, we are in 3D. X, Y, Z. We have some kind of surface right? This is S2, this is S3, and the bottom side is S1, right? So here's the thing, we suppose that it's a type 1 region, meaning that it's kind of, when you project the whole surface, the whole solid, it's gonna give you some solid here, some region here, D. So here we are supposing that it's a kind of, for each point, it's between U1 and U2, right? So this is kind of U2 XY, and this is, right, U1, right? This is the bottom surface is U1, the top surface is U2, and in between them, you have a kind of a vertical translation of all of this. So it's really lines here. These are lines. The lines, right? And when you have this kind of surface with this kind of very specific setting in terms of it's between U1 and U2, the normal vector when you are on the side. So this side here, for example, S3 might not exist. For example, if you have a sphere, right? A sphere doesn't have this kind of S3. S3 is kind of collapsed here, right? But it might happen, right? This is, it can have this kind of surface, right? Well, this is a kind of cylinder. So this is S3 and the bottom will be S1 and the surface will be S3 and this is gonna be the surface, right? But the good thing is about this S3, the normal vector, because as I was saying, these are like vertical lines, the normal will be really parallel or to the XY plane, right? So it's going to belong to the XY plane. We will have no Z component because we're going like upward. We're describing this this solid upward and going from U1 to U2 in a vertical way. So here I'm just going to say, so in case S3 is existent, but you're going to see anyway, it's going to give 0. Observe that on S3, the normal vector is horizontal throughout S3. So N is perpendicular to K. So if it's perpendicular to K, it means that if you want to compute this quantity here, Kn over ds, it would be the integral over S3 of 0 ds, meaning 0. So it doesn't really matter. Now on S2, the surface is given by Z U2 XY. So now if you apply, now we are on S2, right? R, K, N, ds. This is really just the surface integral over S2 of the vector field RK ds, right? Now, if you apply the formula for, this is the vector field F. Now, for this case. Now, if you apply the formula, when you have a graph of a function, as I was saying, just do it by hand. Compute Rx, compute Ry, Ru, Ry, scalar, cross product. You're gonna observe that this one gives you exactly R, X, Y, because of the first Y and G, they're gonna vanish because it has no Y, and because this vector field has no X or Y component. But then you have to evaluate this R in the vector field has to be evaluated on the surface, which in this case is gonna be U2XY. Because remember, this is a function of 3 variables. And then you have to go through the parameter space, which is in this case, the projection on the XY plane. So this is gonna give you this. But then you have to keep track on the fact that when you compute Ru and Rv, you are using, see if you use the formula I gave you, it uses the fact that it's the normal vector has a positive component, right? Now, if you use the same formula on S1, it will give you the positive component. And here's the trick. Here's the tricky part, in the sense that if you use the formula, now this is okay. This is okay for S2, right? This is for S2. This is the formula. You integrate. We're done. Now on S1. Now, if you want to use the same formula I gave you for the surface integral on S1, what will happen is if you use it directly, it will compute the surface integral on S1, but with the orientation given like this. Because remember, it was the formula I gave you was always for the positive orientation, meaning that the key component is always positive. So make sure that you understand this part, right? Because the graph of a function is when S is the graph of a function, the key component will be 1 or -1, right? So if in this case it's going to be 1, it'll give you the positive one. It's going to give you the 1, but that is not the right one to take because this is a closed surface. So the right one is, in this case, is the one that points downside, like outside, outward, right? Because this is the positive orientation, right? So this is the green one. That's the right one. That's the right one because we are going, remember, when it's closed surface, it's always the positive orientation that goes outward. So when you apply the formula here, it's exactly the same formula, but except that when you're going to compute this ds, right, you have to take minus that one. So on S1, we have z equal to u1 xy, but on this surface, the normal vector point, because if it was a separate surface, just S1, you have the choice to choose whatever you want as an orientation, unless we're going to specify in the exercise. And the formula you have and the formula you use is for the specific orientation where the k component is positive. The normal vector points downward. So, and again, what's the reason? The reason is because when you're going to multiply, when you're going to compute Ru, Rv, you have to take the other side, which is minus, right? So that's the reason you have to multiply by minus. So we multiply by -1 using the same formula. And by the same formula, I'm talking about these two here. So the integral over S1 of Rk ds, it's minus the integral over d r xy evaluated on the surface, which will be xy dA, right? So now if you want to gather all this information together, so the integral over S of R, K, and ds is the integral over S1 plus same thing, right? S2 ds plus the integral over S3 ds, right? And we computed all of these. So it's integral over d of r xy u2 xy minus r xy u1 xy dx dy, right? Which is the same thing as the integral over e of d r dv, right? This is the same as, right? If you go back, that's why we use this right here, right? So it works, right? Now, so that's it. This completes the proof. This completes the proof. So this completes. Whew. Okay, so this completes the proof and it also completes the class itself. So that's it. That's all what you need to know about the class. I'm glad we made it. We were on time, exactly on time. So make sure you understand all of this. Make sure you email me, you post on Piazza. Make sure you send emails if you have any questions. And thank you for attending the classes. I am pretty sure that you're gonna be doing well because you attend the class. Because when you're gonna have an advantage. That's not a time wasted. And thank you for your attendance. And if you liked the way I teach the class, that was the first time I teach the class. So it was my first class ever. It was online. So if you like the way I teach, if you have any comment or you have anything to add or say thank you or you're awful or you're amazing, whatever you want, say, complete the form that's gonna send I hope that was sent to you, a kind of form to evaluate the course. And thank you again. All right. Okay. So good luck with the assignment 4 and good luck with the rest of everything. It was a pleasure to teach this class. Okay. Thank you. All right. Have a nice week, everybody.